All right, so it seems that we are ready for the last talk of this afternoon. Sanders, triangular geometry applications to spectral Mackey functors.
Okay, well, thanks for the introduction. I'm very happy to be speaking today, and I'm grateful for the opportunity. So hopefully there won't be any technical issues, and hopefully you can hear me clearly. If I cut out or anything, please just interrupt me. And if there are any questions you have, please feel free to just unmute yourself and interrupt me. I'm happy to answer any questions that might turn up. So let's begin at the beginning. So as we know, in mathematics, we are confronted with wild classification problems. So for example, there's essentially no hope for us to classify all finite dimensional representations of most finite groups in positive characteristic. For most finite groups, classifying all its representations is a totally wild problem. Similarly, we essentially have no hope to classify all finite CW complexes up to homotopy equivalence. It's another kind of classification that ideally we would like, but we really have no hope of actually succeeding in achieving it. And of course, there are many more kinds of classifications that we would like, but we really don't expect to be able to solve. So with this in mind, kind of with this awareness that we have these very wild classification problems, a very kind of important development of the last 30 years or so was the realization that nevertheless, it often is possible to classify such mathematical objects up to a weaker notion of equivalence. So what we do is we work stably. So that is, we work in a suitable stable homotopy category of such objects. And we say that two objects are equivalent if they can build each other using the natural tensor triangulated structure of this stable category. So you kind of take an object and you consider all the objects you can create from it by using suspensions and cofiber sequences and direct sums and tensoring with other objects. By considering the objects that can build each other in this way, you obtain a kind of weaker notion of equivalence of the mathematical objects you're studying. And technically, classifying the objects of your category up to this weaker notion of equivalence technically amounts to classifying the thick tensor ideals of your category, classifying certain subcategories of your category. And the connection there is that two objects, x and y, are equivalent in this weaker sense exactly when they generate the same thick tensor ideal, right? Saying that x and y generate the same thick tensor ideal is saying that x and y can build each other using these tensor triangulated operations. So this is the development that has happened in the last few decades, the recognition that often you can classify the thick tensor ideals, in other words, classify the objects up to this weak notion of equivalence. So the three primary kind of historical examples of such classification theorems, there are three of them. So the first would be the case of the stable module category of finite dimensional representations of a finite group. So the the thick tensor ideals of this category were classified by Benson, Carlson, and Rickard. As another example, we could take the stable homotopy category of finite spectra in algebraic topology. The thick tensor ideals of this category were classified by Hopkins and Smith. And as a third example, you could take the derived category of perfect complexes of a scheme. The thick tensor ideals of this category were classified by Thomason. Now, each of these three classification theorems in these three different settings are obtained by using some kind of notion of support for the objects of the category you're studying. So for example, if we take the classification theorem for the stable module category, this theorem is obtained by using the theory of support varieties, which was developed by a number of people. And this theory of support varieties, what it does is it assigns to each finite dimensional representation of your group a certain closed subscheme of the projective scheme associated to the group cohomology ring. So you're assigning these closed subvarieties to every finite dimensional representation, and this allows you to start reasoning kind of geometrically about representations in terms of these closed subschemes. And this led then to a classification of finite dimensional representations up to this weaker notion of equivalence, because they were able to prove that two such representations are equivalent in this weak sense exactly when their support varieties coincided. But this is a general kind of business. So if we take the example of the stable homotopic category of finite spectra, the thick tensor ideals here are classified using a notion of support for finite spectra, which is defined using the so-called Morava K theories. So we have these historic, sorry, are there any questions at this point? Maybe I should ask. So we have these historic examples of classification theorems, and they were kind of greatly clarified by the work of Balmer, who introduced the universal notion of support for essentially small tensor triangulated categories. So let me say something about his construction. So what Balmer did is he gave this construction which associates to any essentially small tensor triangulated category a certain space, the spectrum, the Balmer spectrum of that space, of that category. And the way it's defined is, well, the points of the Balmer spectrum are the prime thick tensor ideals of your category. So it's kind of defined in a way quite analogous to the prime ideal spectrum of a commutative ring, except you're dealing with a tensor triangulated category instead of a commutative ring. So the points are the prime ideals, and you can define a topology on it. So you get this topological space. And then one can then define for every object of your category, every object X, a certain closed subset of this space. This is how it's defined. It's not so important. The point is just that you define for every object of your category a certain closed subset, its support, which lies in this topological space. And this assignment of closed subsets to the objects of your category satisfies a number of natural conditions you might expect. So for example, the support of the zero object is empty, and the support of a direct sum of two objects is the union of the supports of the individual objects. And there's a list of kind of properties that this notion of support has. But the conceptual way of thinking about this construction is that this space, the Balmer spectrum, equipped with this notion of support for the objects of K, is the universal such thing. So the Balmer spectrum satisfies a universal property. It's the universal space equipped with a well-behaved notion of support. A well-behaved meaning a notion of support satisfying a number of natural axioms. And so this is actually one way you can kind of conceptually think of the Balmer spectrum. It's giving you the universal notion of support for the objects of your essentially small tensor triangulated category. And what this universal notion of support gives you is that it always classifies the objects of your category up to that weak notion of equivalence. So this is the kind of abstract thick subcategory classification theorem due to Balmer, which says that under very mild hypotheses on your tensor triangulated category K, there is a bijection between the thick tensor ideals of your category and certain subsets of this space. And this map is given by sending a thick tensor ideal to its support, so the union of the supports of all the objects in that subcategory. And so we have on the left-hand side the thick tensor ideals of K. On the right-hand side, we have these so-called Thomason subsets of the spectrum. So what is a Thomason subset? Well, a Thomason subset, if you're not familiar, by definition, it's a union of closed sets where each of those closed sets has a quasi-compact complement. Okay. So it might seem a little strange the first time you see it, but for example, if the space is Noetherian, if the space is a Noetherian space, then this simplifies a little bit. And in that case, being a Thomason subset is just the same as being a union of closed sets. And that's the same thing as being specialization closed. So in a lot of kind of Noetherian contexts, you don't hear so much talk about Thomason subsets, you hear talk about specialization closed subsets. But in any case, you always have this abstract classification theorem giving you a classification of the thick tensor ideals in terms of certain subsets of the Balmer spectrum. And so from this point of view, the original task of trying to classify the objects of our category up to this kind of weaker notion of equivalence gets transformed into the problem of giving some kind of explicit description of this space, giving an explicit description of the Balmer spectrum and describing this universal notion of support. So for example, just to reiterate, if you can do this, well, two objects of your category are going to be equivalent in that weak sense precisely when they have the same support. So this kind of is generalizing what was what turned up in modular representation theory. So if we look at the examples that I previously mentioned, for example, if we take the derived category of perfect complexes of a commutative ring, we can consider the Balmer spectrum. And what we get is we just recover the ordinary prime ideal spectrum of the commutative ring. Similarly, if we take the derived category of perfect complexes of a scheme, so this is just more generally, if we take the Balmer spectrum of the derived category of perfect complexes of a non-pathological scheme, we recover the scheme. On the other hand, if we take the stable modular category of finite dimensional representations, we take the Balmer spectrum, that is exactly the projective scheme associated to the group cohomology ring. So this result here, it's really a nice thing. It's really kind of giving a conceptual explanation for the role that that theory of support varieties and that role that this kind of geometric object associated to the cohomology ring, arising from the work of Quillen, it really is sort of giving a conceptual reason for why that is turning up in the study of modular representation theory. That projective scheme is the Balmer spectrum of the stable modular category. In other words, it's the universal space of supports for finite dimensional representations. That's one way of thinking about it. Okay, so this is all kind of quite nice. We have this goal. We'd like to understand these objects of these categories. We like to understand them up to this kind of weaker notion of equivalence. We can always sort of do that using this Balmer spectrum. All we have to do is sort of understand what the Balmer spectrum is. So kind of conceptually, the theory is quite nice and somewhat well understood. But although all of this is quite nice, it only really applies to classifying the kind of compact objects in these settings. So for example, these classification theorems that I mentioned, they classify the finite dimensional representations. They classify the finite spectrum. They classify the perfect complexes. So they're all about they're classifying objects under some kinds of finiteness conditions. And often these categories that we're talking about arise as the subcategory of compact objects in some much larger, for example, rigidly compactly generated tensor triangulated category, a much larger triangulated category, one that has arbitrary coproducts, for example. And so all of this theory that we've just been talking about, all of these developments, it's really only being applied to this subcategory of compact objects in this um, larger category. For example, we have the big stable module category of all representations, not necessarily finite dimensional representations. Similarly, we have the stable homotopy category of all spectra. Similarly, we have the kind of unbounded derived category of a ring. We take arbitrary complexes of arbitrary R modules with no kinds of boundedness or finiteness conditions. And so these categories that we've been talking about, which have these classification theorems, they're all just sitting inside these larger tensor triangulated categories. And, well, many of the most interesting objects are not compact. Many of the most interesting objects actually are objects that lie in these bigger categories and not in these smaller ones. So, for example, if we take the stable homotopy category, by Brown representability, every cohomology theory is represented by a certain object in the stable homotopy category. But those objects that represent cohomology theories are infinite dimensional things. They're not finite spectra. And so if you want to understand sort of cohomology theories, just talking about finite spectra is not really going to cut it. You want to understand the big objects, the non-compact objects of this bigger tensor triangulated category. So that's the thing. What about the big objects? We want to understand these objects, these non-compact objects in these big tensor triangulated categories T. So technically, what we would like to do is we'd like to classify the localizing tensor ideals of this big tensor triangulated category. So a localizing tensor ideal, this is a triangulated subcategory that's closed under the tensor. It's a tensor ideal, and localizing means that it's closed under arbitrary coproducts. And so just like previously trying to understand the compact objects boiled down to classifying the thick tensor ideals of the category of compact objects, when we're dealing with these big objects, we essentially want to classify the localizing tensor ideals of the category. For example, if we could understand the localizing tensor ideals of the stable homotopy category, that would provide a coarse classification of cohomology theories in algebraic topology. It would be something very interesting. Now, we can't apply Balmer's construction to these big tensor triangulated categories. So the first issue is that these big tensor triangulated categories are not essentially small, but such set theoretic issues are not really the main point. That's not really the main issue. The main issue is that the axioms for Balmer's universal notion of support are not appropriate for big objects. So for example, morally, the support of a compact object should be closed. It should be a closed subset. But if we're dealing with an arbitrary object, we don't necessarily expect the support of some infinite dimensional thing to have a closed support. And so Balmer's universal notion of support, it's the universal property it satisfies, it's the universal notion of support satisfying a number of axioms. For example, the support is closed, and the support of the tensor product of two objects is the intersection of the supports of the individual objects. There's a number of natural axioms that Balmer's notion of support satisfies, and it's the universal such thing. But if we're talking about big, non-compact, infinite dimensional things, some of those axioms are not really to be expected. And so that is really more the issue for why we can't apply the previous discussion to these big tensor triangulated categories. Are there any questions at this point? So we can't apply Balmer's construction, but nevertheless, we can still attempt to classify these big objects, these localizing tensor ideals, by using some kind of notion of support appropriate for these big non-compact objects. But as I've sort of alluded to a little bit, um, there are a couple of issues. So, for example, support for big objects is less well behaved, and it's less clear cut what properties such a notion of support should have. Right? It's less clear cut. Um, exactly the axioms one would expect such a support for a big tensor triangulated category to possess. Ideally, we would like a big version of the Balmer spectrum. We would like a universal notion of support for these big tensor triangulated categories, which suitably classifies the localizing tensor ideals. That's what we would like. Unfortunately, no one has achieved in creating such a construction, and there's evidence that in general it can't exist. So I give a few references that you can look up on about that. So we kind of don't have a kind of universal notion of support for these big tensor triangulated categories. There's evidence that maybe such a thing can't exist, but nevertheless, we still try to find useful theories of support for big objects, and people are able to obtain some significant positive results in certain Noetherian situations. So the first example of such a significant positive result is a theorem due to Neyman, going back to the early 90s, where the theorem says that if R is a commutative Noetherian ring, then the usual cohomological support for complexes provides a bijection between the localizing tensor ideals of the big unbounded derived category and the arbitrary subsets of the spectrum of the ring. So the previous kinds of results about compact objects would be telling us that the compactly generated localizing tensor ideals of this category correspond to the specialization closed subsets of spec R, whereas arbitrary localizing tensor ideals are corresponding with arbitrary subsets of spec R. So it's a very clean classification of the localizing tensor ideals. They're just given by arbitrary subsets of the spectrum of the ring. And so this is kind of a prototypical example of the kind of result one might hope to achieve, at least in some Noetherian contexts, classifying the localizing tensor ideals of your big category in terms of the arbitrary subsets of some space. So it's a nice result, and it sort of has guided what to expect going forward. But this assumption that the ring is Noetherian is very important in this theorem. So in general, this statement fails strongly for non-Noetherian rings. So there are examples of non-Noetherian rings for whom the spectrum is just a single point, and yet which have many localizing tensor ideals. So what we should take away from this is that without some kind of Noetherian assumptions, we don't really have much expectation of having such a nice classification of the localizing tensor ideals, or at least not, or at least it's kind of wide open what one might expect without any kinds of Noetherian hypotheses. Now, the most kind of notable and prominent approach to classifying localizing tensor ideals comes through the work of Benson, Iyengar, and Krauser. So in a sequence of papers going back a few years, Benson, Ingar, and Krause introduced a notion of support for um, big, so compactly generated triangulated categories that are equipped with an action by a Noetherian graded commutative ring R. So given a compactly generated triangulated category equipped with such an action, they constructed a notion of support for the objects of the category. And what they do is they assign to each object a certain subset of the spectrum of that graded commutative Noetherian ring. Okay, so they're defining a notion of support for the objects of T as subsets of the spectrum of this ring that's acting on the category. So I'm not going to go into the details, but I'm just kind of bringing this up, reminding us about this work of Benson, Ingar, and Krause. Now, for example, if T was a tensor triangulated category, then what we can do is we can take the unit object of the tensor and take the graded endomorphism ring of the unit object. The graded endomorphism ring of the unit object is a commutative graded ring, and it acts on the category. So for a tensor triangulated category, there's always this canonical action of the endomorphism ring of the unit on the category. And so if T is a tensor triangulated category, we can apply the theory of Benson, Ingar, and Krause to the canonical action of the endomorphism ring of the unit, well, provided this endomorphism ring is Noetherian. Now, in general, this support theory of BIK does not always classify the localizing tensor ideals of T, right? It's too much to hope, that in this level of generality that you would get such a classification. But they develop a powerful condition called stratification, which is sufficient to obtain such a classification. So in general, you can't expect this theory of support will work, but they develop this condition that will ensure that this notion of support will classify the localizing tensor ideals of the category. So we'll return to this a little bit. Another approach for defining a notion of support for big objects of big tensor triangulated categories. Oh, okay, maybe I should mention that, so BIK developed this theory of stratification, and they applied their theory to classify the localizing tensor ideals of the big stable module category of all representations for all finite groups. So this was a big application of their theory of stratification, their approach to classifying localizing tensor ideals. And but since that time, there have also been quite a lot of additional applications of their theory to stratify other categories that are of interest. So their theory has been quite successful in classifying localizing tensor ideals of big triangulated categories. Now, another approach for defining support for big objects of big tensor triangulated categories was introduced by Balmer and Favi. And so let me start off by just kind of giving an overview of this, what Balmer and Favi do, and then we'll give a few more details about it. So basically, what Balmer and Favi do is they introduce a notion of support for rigidly compactly generated tensor triangulated categories. So the Benson, Ingar, and Krause stuff kind of also held for triangulated categories that don't have a tensor structure, but that just have a ring acting on it. Now we're really focusing on just tensor triangulated categories. And this notion of support for rigidly compactly generated tensor triangulated categories assigns to each object a certain subset of the Balmer spectrum of the subcategory of compact objects. So I've just mentioned before that we can't talk about the Balmer spectrum of this big category T. Nevertheless, we can still consider its subcategory of compact objects and consider the Balmer spectrum of that essentially small tensor triangulated category. And so this notion of support introduced by Balmer-Favi, it lives in the Balmer spectrum of the subcategory of compact objects. So that's kind of where the notion of support is living. And well, it does still require some Noetherian hypotheses on the space in which the support lives in order for it to be well behaved. But under those hypotheses, this notion of support introduced by Balmer-Favi, it extends the universal notion of support for compact objects, right? For a compact object, we have the universal notion of support, which is a certain closed subset of this space. This thing that Balmer-Favi have done is sort of extends that to a notion of support for not just the compact objects, but the arbitrary objects of the category T. And this notion of support was then developed further and applied to the problem of classifying localizing tensor ideals by Greg Stevenson. And so Greg has done a lot of work on this notion of support and kind of applying it to understand tensor triangulated categories. So let's now give a little bit more detail about this Balmer-Favi approach to support. So from here on out, T is always just going to be a rigidly compactly generated tensor triangulated category. We're going to take a kind of geometric perspective, the kind of geometric perspective of tensor triangular geometry. We're going to think of this big tensor triangulated category T as sort of like a bundle or sheaf of tensor triangulated categories that lives over this space, the Balmer spectrum of its compact objects. Okay, that's kind of the geometric perspective we're going to be having. And we're going to assume that this space is so-called weakly Noetherian. So what do I mean by weakly Noetherian? So weakly Noetherian is a topological condition which generalizes Noetherian and also generalizes being profinite, a profinite space. So it's a kind of common generalization of Noetherian spaces and profinite spaces. And by definition, what it means is that every point is weakly visible. What does that mean? Well, by definition, a point is weakly visible if the singleton set consisting of that point can be realized as the intersection of a Thomason subset and the complement of a Thomason subset. So there exists a Thomason subset and the complement of a Thomason subset that if we intersect them together, we single out the point P. So if that's the case, we say that the point P is weakly visible. And if every point is weakly visible, we say that the space is weakly Noetherian. Now, it might seem like a little bit of a strange definition the first time you see it, but what it allows you to do is sort of intuitively, you can isolate the point P as a combination of a finite co-localization. The co-localization sort of restricts to the kind of part of the category that lies over Y1. And then you do a finite localization, which sort of restricts to the part of the category that lies over the complement of the second Thomason. And so by doing a kind of co-localization and a localization together, you're sort of intuitively isolating the point P. And so this is similar to how Benson, Egar, and Krause kind of approach defining support. And so you then can define this object, GP, and tensoring with this object is kind of affecting these two things, this co-localization and this localization. So tensoring with GP is sort of like narrowing down to the point P. And so you can think of the category obtained by tensoring everything with GP kind of like the stalk of the category at P. And we can then define the support of an arbitrary object as consisting of those points, those primes, those stalks where the object is non-zero. And so in summary, we have, if we assume that the spectrum is a weakling theorem space, we have this notion of support sitting inside the Balmer spectrum of the subcategory of compact objects, and it extends the universal notion of support for compact objects. So what do we do in this project? I've realized that time is running by way faster than I expected. So in a recent project joint with Tobias Bartel and Drew Hurd that we kind of put on the archive very recently, about a week ago, what we do is we systematically develop a theory of stratification based on this notion of support, this Balmer-Favi notion of support, which is based on the Balmer spectrum. So we kind of systematically develop an approach for classifying localizing tensor ideals using this notion of support. And we will clarify the relationship between this approach to stratification and the previous work of the previous theory of Benson, Egar, and Krause. And we apply this theory to new examples, notably in equivariant homotopy theory. So let's say a little bit more about what we mean by stratification. So following Benson, Egar, and Krause, we say that the big tensor triangulated category is stratified if it satisfies two conditions. The first, which is called the local to global principle, says that morally, basically every object can be reconstructed from its germs. Or technically, it's saying that every object is in the localizing tensor ideal generated by these germs. So it's saying that T can be reconstructed from these things. And the second condition is what we call minimality. So the second condition is saying that for each point, this stalk ideal is a minimal localizing tensor ideal. It's a non-zero localizing tensor ideal, and there's no localizing tensor ideals contained in it. And so these are the two conditions that Benson, Egar, and Krause kind of identified as being sufficient to classify the localizing tensor ideals. So that's given by the following theorem, which says that the following are equivalent. The first is that those two conditions hold, that the local to global principle holds, and we have minimality at all points. And the second condition, the second equivalent thing is that this notion of support provides you a bijection between the localizing tensor ideals of your category and the arbitrary subsets of the space, the Balmer spectrum of compact objects. So if you have those conditions, you get this classification of the localizing tensor ideals. And in fact, this classification of the localizing tensor ideals is equivalent to those two conditions. So in other words, stratification is equivalent to this kind of classification of the localizing tensor ideals. Now, the first kind of obstruction to obtaining such a classification is that your category might not satisfy the local to global principle. And indeed, the local to global principle does not always hold. Examples of that have been given by Greg Stevenson. But one thing we do in this paper is we improve some results of Greg's to prove the following theorem, which says that if the spectrum is a Noetherian space, then the local to global principle always holds. And so this is an improvement on results in the literature. Previous results in the literature had some sort of unnecessary hypotheses. They had to assume that there was an underlying model and so on and so forth. And this is a kind of much cleaner statement. And it's actually quite useful. It says that, in a lot of generality, we always have the local to global principle. We don't have to worry about it. And so the question of stratification is just going to boil down to this minimality of these stalk ideals. So maybe I will just jump over this slide. Basically, another thing we do in our paper is we also analyze some of the consequences of what happens if your category is stratified, and there are various consequences. You get a complete description of the Bousfield lattice of your category. We also clarify that if your category is stratified, then the telescope conjecture holds, provided the spectrum has this topological condition of being generically Noetherian, which is another topological condition which simultaneously generalizes Noetherian and profinite. This is strengthening and generalizing a theorem of Greg Stevenson. But since I'm running out of time, let's not talk about that anymore. What I'd like to very briefly mention is that this theory of stratification we develop has a number of nice features. And I'd like to very quickly mention some of these nice features under the following three headings: universality, permanence, and generality. So first of all, universality. So what we prove in a slogan is the following: that the Balmer-Favie notion of support provides the universal approach to stratification in weakly Noetherian contexts. So more precisely, we have the following theorem. Suppose we have a notion of support for the objects of our category, which lies in a weakly Noetherian space. So suppose we have an assignment of a subset of this space to every object of our category, and suppose this assignment, satisfies some very mild hypotheses. If this notion of support stratifies the category, meaning classifies the localizing tensor ideals, showing that the localizing tensor ideals correspond to the arbitrary subsets of the space X. So if you have a notion of support in a weakly Noetherian space, which stratifies the category in a way that is compatible with the usual classification of thick tensor ideals of compact objects, then there's a unique identification with the Balmer-Favie notion of support. Your space is homeomorphic to the Balmer spectrum of compact objects, and your notion of support is, under that identification, the Balmer-Favie notion of support. So this theorem is a uniqueness theorem rather than a kind of universal property. But philosophically, the result is that this theorem is telling you that if you have a category T, and if the localizing tensor ideals of your category can be classified by a reasonable notion of support lying in a weakly Noetherian space, then the Balmer-Favie notion of support will do the job. And so in that respect, the Balmer-Favie notion of support is sort of like the universal choice of support for trying to classify your category. So as a corollary of this uniqueness result, we have, for example, the following theorem, that if T is a tensor-triangulated category that is stratified in the sense of Benson, Iyengar, and Krause by the action of a graded Noetherian ring, well then the BIK space of supports is canonically homeomorphic to the Balmer spectrum, and the BIK notion of support coincides with the Balmer-Favie notion of support. So in other words, in any example of a category where we know it's stratified in the sense of Benson, Iyengar, and Krause, then it follows that it actually is also stratified by this Balmer-Favie notion of support lying in the Balmer spectrum. Another feature of our theory of stratification is that it exhibits good permanence properties under changing categories. And so, for example, it satisfies versions of Zariski and étale descent. So, for example, we have the following theorem. Suppose that T satisfies the local to global principle. For example, by our previous theorem, suppose that the spectrum is Noetherian. Then if we have a cover of our space by complements of Thomason subsets, then the category T is stratified if and only if each of the categories over each of those subsets is stratified. So for example, you could apply this to a cover by quasi-compact open sets. So this is, for example, showing that being stratified is sort of Zariski local. You can check it on a Zariski cover. So this already appeared in the work of Greg Stevenson, that stratification is kind of Zariski local. But we can push this a little bit farther because complements of Thomason subsets are more general than just quasi-compact open sets. They include arbitrary intersections of quasi-compact open sets. And so a consequence of this theorem is actually that rather than reducing the problem of stratification to an open cover, it actually allows us to reduce the problem of stratification to the local categories at each point. And this is actually more subtle than it might seem because, for example, the local to global principle is not something that can be checked each prime at a time. But combined with our previous theorem that gives us the local to global principle in a lot of generality, that allows us to really kind of reduce the problem of stratification to the local categories at each point. So to work a prime at a time. And this is a very useful aspect of our theory. Another thing our theory has is it satisfies a kind of weak form of finite étale descent. In the interest of time, I'm going to skip over this. But basically, let me just say that basically it allows us to, in some circumstances, establish stratification for a category we're interested after passing through a finite étale extension. And this is really important for our equivariant applications. So this is a kind of, there's an étale business going on here that can be useful. The other thing I want to emphasize about this theory of stratification is that it's very general, right? And it provides a uniform perspective on old and new classification theorems. So for example, let me state the following theorem, which says that the following categories are stratified, meaning stratified by the Balmer-Favi notion of support. Well, big stable modular category of a finite group. This is due to Benson, Iyengar, and Krause. Derived category of a Noetherian scheme. It's due to Greg Stevenson. And the resulting classification of localizing tensor ideals you obtain actually was originally due to Alonso Tario, Jeremias Lopez, Suto Solario. Another example would be the category of EN local spectra in algebraic topology. This is essentially due to the work of Hoppe-Strickland. And finally, we can take the category of rational G spectra for any compact Lie group. And this resulting classification of localizing tensor ideals is due to John Greenlees. So we have these four examples of categories that they're quite different, and yet they're all sort of stratified in this sense by this Balmer-Favi notion of support. Now let me clean up this statement a little bit, just so we have these four examples. Now it might seem like this is just a kind of repackaging of known classifications in the literature, and in some sense that's true, but there still is some kind of new mathematical content here, because this theorem implies that the different notions of support that these authors were using to classify the localizing tensor ideals in these different examples, it follows that those notions of support coincides with the Balmer-Favi notion of support. And so what you're getting is that certain notions of support that are defined in a certain way, it turns out that they're equivalent to a notion of support that's defined in a quite different way. So there is some kind of new mathematical content to this theorem. And the other thing worth also emphasizing here is that none of these four examples are canonically stratified in the sense of BIK. Right? So if you take the derived category of a non-affine scheme, that's not obviously stratified by any action of a affine scheme. Similarly, for these last two examples, there's no ring acting on these categories that is going to classify the localizing tensor ideals. So these are examples that don't really fit into the theory of Benson, Ingar, and Krause, but they are stratified by this Balmer-Favi notion of support. So all of that's cool, but what we do is, we don't just develop this theory of stratification for its own sake. We also apply this theory we developed to completely new examples, notably in equivariant stable homotopy theory. So I'm kind of run out of time, but let me try to very briefly say what I wanted to say. So let's let SHG denote the equivariant stable homotopy category. Now, through the work of a number of mathematicians, we have a pretty good understanding of the Balmer spectrum of the equivariant stable homotopy category. We completely understand it as a set, and there are some very interesting questions that remain about its topology. So we understand it as a set, but there are some kind of questions about its topology that remain unresolved. But if we consider this category, SHG, I mean, it's a highly non-Noetherian category, even for G equals 1. So even the non-equivariant stable homotopy category, it's a highly non-Noetherian category, and sort of the classification of its localizing tensor ideals is a completely wide open problem, completely kind of wild thing. So with that in mind, what we might try to do to gain some understanding, some deeper understanding of stable homotopy category and the G equivariant stable homotopy category, is to study certain kinds of linearizations and truncations of this highly non-Noetherian big category. And so, for example, a linearization, or maybe the linearization of the G equivariant stable homotopy category would be the category of derived Mackey functors that I believe Irakli spoke about. And a truncation of SHG would be, for example, the category of En local spectral Mackey functors. For example, if you took n to be 0, you would obtain the category of rational G spectra. So the category of rational G spectra is sort of like the most brutal truncation, but you could consider other chromatic truncations. And so since SHG is a pretty big, non-Noetherian, complicated thing, we could instead consider these categories of Mackey functors, or spectral Mackey functors, and see if we could understand them. And that's what we achieve as our kind of main, completely new application of this theory of stratification. We are able to completely classify the localizing tensor ideals of the derived category of Mackey functors and these categories of En local Mackey functors, these which I'd like to think of as linearizations and truncations of the G equivariant stable homotopy category. And so maybe skipping this discussion of spectral Mackey functors, so sort of the theorem we prove is that if G is a finite group and E is a commutative ring spectrum whose derived category, the spectrum of the derived category is Noetherian, we prove that if the derived category of that ring spectrum is stratified, then so is the category of spectral Mackey functors with coefficients in E. That's the theorem we prove. And the proof of this theorem really demonstrates the power of this theory of stratification. It really, requires using this kind of theory that we develop, and we get as corollaries, if we take E to be the Eilers-MacLane spectrum of the integers. In that case, we're just dealing, the hypothesis is that the derived category of integers is stratified, which it is by the result of Niemann. And so we obtain a classification of the localizing tensor ideals of Dirac-Mackey functors. If we apply it to the En local sphere spectrum, we can apply the theorem and obtain a classification of the localizing tensor ideals of the category of En local spectral Mackey functors. And so those are kind of the main new applications we get. I think they're quite interesting given the complexity of the whole equivariant stable homotopy category. And one thing maybe I should point out, though, is that if we think about the Balmer spectrum of these categories of spectral Mackey functors, we kind of understand what they're like as a set, for all finite groups and for any ring spectrum E. But there are kind of interesting questions that remain about the topology. For the case of the Eilenberg-MacLane spectrum of the integers, for the case of the derived Mackey functors, those topological questions are resolved in this joint work with Irakli Pachakoria and Christian Wimmer. We're able to completely compute the spectrum. And there's a very nice answer that the spectrum of the category of this linearization sort of captures precisely the height 0 and height infinity chromatic layers of the equivariant stable homotopy category. On the other hand, if we go to the category of En local spectral Mackey functors, we understand the Balmer spectrum as a set, but there are some unresolved questions about its topology. We can show that the Balmer spectrum bijects onto the kind of height less than or equal to n layers of the equivariant stable homotopy category. So it is this kind of truncation, but we can't prove that this continuous bijection is a homeomorphism. So there's sort of some unresolved questions about the topology. And so let me just say 1 minute to kind of summarize that our approach to understanding big tensor triangulated categories involves 2 steps. First, it's a property of the category whether or not it is stratified. There's no auxiliary actions, there's nothing, it's just a property of the category. If the category is stratified, then we obtain a classification of the localizing tensor ideals, which is given in terms of the underlying set of the Balmer spectrum. And then what we can do is we can try to determine the topology of the Balmer spectrum. And if we can do that, we would obtain the classification of thick tensor ideals of compact objects. And what this example of En local spectral Mackey functors gives us is it gives us an example where we can completely classify the localizing tensor ideals, but we actually don't have a classification of the thick tensor ideals of compact objects because of unresolved questions about the topology of the Balmer spectrum. So this kind of flips things on the, a little bit differently than how things usually work, where you first try to understand the compact stuff and then try to deal with the big stuff. And this is saying that in some sort of Noetherian contexts, one could argue that in some sense, classifying the localizing tensor ideals actually is easier than classifying the thick tensor ideals of compact objects. Anyway, I think I'm out of time, so I better stop here.
Thank you. Questions?
Sorry, I didn't hear that.
I mean, can I ask? I mean, if nobody has a question, so yeah. So like, if we take instead of Z some ring R in general, do you guys in that case understand the full topology, depending on obviously taking into account the topology of the
so if you take R to be a Noetherian ring, we stratify the localizing ideals. But for the topology, no, we don't get the topology. So it's we I mean, we don't really try, but we don't get the topology.
And then, of course, the ring spectrum example you provided, which is not a ring, is very difficult, right? I mean, it's LN local sphere is a tricky one. But what if you take some and like say, let's not do non. I mean, okay, you're already taking non-connective things, so maybe I can even ask that. So what about like say big KU or small KU or these kind of gadgets?
Right. So the question then becomes so
In a way, also related to what Ivo and Greg did at some point when looking at the I think a Balmer spectrum for like graded rings with those.
yeah. Yeah. So again, we understand the spectrum as a set. You know, basically in general. You know, I mean, you're going to have in terms of the spectrum of the non-equivariant thing. You know, and so if you understand the spectrum of the non-equivariant thing, then you get a description of it.
That was general. You said as a set, right?
Yeah. So that's in general. Now, however, the topology is not resolved. Topology is not resolved. There are unresolved questions about how to deal with the topology for these examples.
Mm-hmm.
And so as you know, I mean, so we sorted that out for HZ, right? But what, you know, we had to do some work, right, to sort that out.
We had to work even in the easiest sort of.
Yeah, exactly. And in fact, and we were able to achieve what we did because sort of there was this you know, kind of truncation of the chromatic information. You know, we were just dealing with the height infinity and height zero. And yeah, in general, it's not clear what goes on with the topology.
Even for these kind of very classical non-ring.
I mean, someone could study it. I mean, someone could study it, but it sort of doesn't come out formally.
Wonderful questions to look at. I mean, it's,
yeah, I think they're wonderful questions too. Yeah, I think that they're really interesting.
Cool.
And this question we have about the EN local things. Yeah, so it's sort of like Tobias, Drew, and I, we're kind of a little, on the one hand, we're a little embarrassed that we're not able to, you know, the spectrum of this category, it bijects. There's a continuous bijection onto the kind of less than equal to n chromatic layers, right? We can't prove that it's a homeomorphism. I mean, it must be. I mean, it must be. There's no God if it's not. I mean, but we can't prove it. And we conjecture it in our paper. So if someone is able to, I think it's a nice conjecture to try to prove.
Something about BKU. Let's read this. It might be fine because there are only two consecutive layers where things can interact.
Yeah, it could be doable. It could be doable.
So maybe that's the first case to look at somehow.
Yeah, it could be interesting. Nice. Sorry, Amula, do you have a question?
Thanks, Beren.
Yes, just sort of very elementary question, if you like. I mean, is the Grothendieck site something that this technology can be applied to? And if so, what would be the stratifications or the grading?
So I'm not sure if I completely understand exactly what you're getting at, but I mean, we sort of, you know, we're thinking of these tensor triangulated categories sort of morally as kind of geometric objects, like categories lying over this space, right? This kind of Balmer spectrum. And there's certain kind of geometric moves we can do, like we can kind of localize the category over an open set. And we also understand kind of what it means to be kind of an étale extension in this world. And so we can start to say some things about kind of the étale site of a tensor triangulated category and how that relates to the problem of stratification and localizing tensor ideals. But even there, sort of for the étale site, our kind of results are not complete. You know, we're able to establish kind of some weak versions of étale descent for stratification, which are sufficient for our equivariant applications. But I don't feel like we have the definitive kind of statement for those kinds of descent results for stratification. And I think that in future work, we will be considering more general descent type statements for stratification. So I'm not sure if that was getting at what your question was asking.
Yeah, I was just sort of trying to find out whether in this theory, say the ordinary Grothendieck site as defined by Grothendieck himself, would it have a single grading or would it become graded with the technology of that you apply?
I don't think I know the answer to that, unfortunately.
Okay, thank you.
You talked about EN local spheres. What about KN local spheres? Does it make any difference to?
So, okay, so yeah, it does make a difference. And so what comes up is the issue that KN localization is not smashing. So localization with respect to EN is a smashing localization. And that means that sort of the category of EN local spectra, it's a really nice category. It's rigidly compactly generated, and that means that also when you go to the equivariant world, things kind of work very easily. So, for example, the category of EN local spectral Mackey functors, you can interpret that category in a few ways, but in particular, it's a smashing localization of the G equivariant stable homotopy category. If you then try to consider, say, KN local things are a little not. You need to be much more careful about how you move things around and so on. And we haven't spent a lot of time considering that case. It would be interesting, but I think that you're going to have to be quite careful about again, all the hypotheses that you have in your theory and so on and so forth. Because another issue, I mean, I guess I feel bad saying this because it kind of shows the limitations of our theory, but I guess we developed this whole theory kind of in the context of a rigidly compactly generated tensor triangulated category. And the KN local category is not an example of such a thing.
But if you restrict it to finite spectra, then it is smashing, I think.
It coincides with
Yeah.
the other localizations on finite spectra, but it's not smashing. I mean, smashing has to do with the big stuff.
Yeah, that's right. On a follow-up, because you're talking about G equivalent stuff, there are, I don't know about EN, but for example, Morava K theory could be of two kinds, one with a non-trivial G action and one with a trivial G action. There are variants of various Morava K theories equivalently. Have you considered what difference
I think that at least for us, in the kind of work surrounding these kinds of equivariant questions that have appeared in my work, the way that the Morava K theories have typically arisen has been still purely non-equivariantly, in the sense that the way they've arisen is that we have passed from the equivariant world to the non-equivariant world by, say, a geometric fixed point functor or something, and then done the non-equivariant ordinary Morava K theories. So equivariant versions of the Morava K theories have not appeared in this work, at least not to my knowledge, and I've written. So I'm not sure how those kind of equivariant Morava K theories may play a role in these kinds of questions, but to date, they haven't really appeared. It's more being sort of passing back down to the non-equivariant world and then using the ordinary Morava K theories. But it would be an interesting thing to understand how those equivariant Morava K theories are.
Your theorem is also just like modules over E, equivariant modules over E with trivial action, right? The left inflation is as we learned at some point. Yeah.
Yes.
Cool. Thanks.
Beren, can I ask another question, please?
Yes.
First of all, thank you. It was a very nice presentation, and I like sort of this new direction, of course. Just about that slide, which we can see now, the spectral Mackey functors, do you have, I mean, how is the stratification achieved? I mean, do you have residue field objects in that case, or what? what is used?
How we prove it? Yeah. So how we prove it is so stratification okay, we have the local to global principle for free. And so we just need to check minimality, right, at all the points. And so to do that, what we do is we pass to smaller subgroups by doing a kind of finite étale extension. So let's choose a prime, let's say, and the prime is associated with a subgroup H and then some kind of thing. So let's say it's like PHC. So this is a prime in our category, and we need to check minimality at that prime. So first what we do is we restrict to the subgroup H. That's a finite étale extension, and we have a theorem that shows that we can establish minimality of this prime in the equivariant category over H. And then, so now we're dealing with a prime which is associated to the whole group itself, right? Now we're dealing with like PG, right? The subgroup is now the whole group, and we need to check minimality there. And so to do that, we go to the local category at that prime, and we just need to check minimality at the local category. And the passage to the local category at the prime for the whole group G itself, that is the geometric fixed point functor. That the passage to the local category, that's a finite localization, that is the geometric fixed point functor. And so the local category we get is just like the derived category of it's like we get to the non-equivariant category basically, and we have stratification there. That's where this hypothesis that the non-equivariant thing is stratified. So we basically pass through these ways down to the local categories, and the place we land is stratified from this hypothesis. I think it's a nice proof.
Yeah, thank you. I mean that explains it very well. Thank you.
Yeah. And one thing I just wanted to mention, since Henning is here, the last slide I wanted to emphasize is that, so I think that this theory of stratification, kind of based on the Balmer spectrum, it's quite flexible. It can be effective even when we don't have a complete understanding of the Balmer spectrum, as this example of EN local spectral acupunctures gives. And this sort of also helps distinguish this notion of stratification from that of Benson, Egar, and Krause, because stratifying in the sense of Benson, Egar, and Krause, it's both weaker and stronger than this kind of stratification, because stratifying in the case of Benson, Egar, Krause, it's classifying the localizing tensor ideals and computing the Balmer spectrum in terms of spec R. So it's kind of stronger and weaker. And yeah, so that's something that I think is worth mentioning. But I guess the point I'm trying to make is that there is some flexibility in sort of not doing that second step, because you can kind of still get some results without having a complete knowledge of the Balmer spectrum. That's what I would say.
Thank you. If there is no more questions, we thank our speaker, Beren, again.